In this module, we are going to discuss about polarimetry. Most physical properties of enantiomers such as melting point, boiling point, refractive index are identical. But enantiomers differ in optical activity. This effect was first discovered in 1808 by E. L. Malus. He passed light through a reflective glass surfaces. In 1811, this is observed in quartz by D. F. Arago. 4 years later, J. P. Biot found that the extent of rotation of the light depends on the thickness of the quartz plates that he used. He also discovered that the other compounds, turpentine and sucrose solutions, were capable of rotating the light. He attributed this optical activity to certain features in their molecular structure, which is defined as asymmetry. Based on his research, he designed one of the first polariscope and formulated the basic quantitative laws of polarimetry. In 1850, Villamy used polarimetry to study the reaction rate of the hydrolysis of sucrose. In 1874, Van 't Hoff proposed that a tetrahedral environment of the carbon atom could explain the phenomenon of optical activity. Today, polarimetry is used routinely in quality and process control in the pharmaceutical industry, the flavor, fragrance, and essential oil industry, the food industry, and the chemical industry. Polarimetry technique measures the optical activity of a chiral compound. This technique measures the change in the direction of vibration of polarized light when interact with it. If we know the angle of rotation of the plane polarized light, different parameters can be defined such as specific rotation, concentration of sugar content. The optical purity of the product also determined by measuring the specific rotation of compounds like amino acids, antibiotics, steroids, vitamins, lemon oil, various sugars and polymers, and comparing them with the reference value if the specific rotation of the pure enantiomer is known. The principle behind the polarimetry is polarimeter measures the rotation of polarized light as it passes through an optically active substance and the tendency of the molecule to rotate the plane polarized light towards clockwise or anti-clockwise direction whose extent of the rotation can be measured. These compounds are called as optically active compounds or substances. Optical activity is unique character for a molecule. Let us see how polarimeter works. A light from the source, usually a sodium vapor lamp, falls on the polarizer. In polarimeter, nickel prism is used as a polarizer. We know in ordinary light, all the waves vibrates in all the directions. But plane polarized light vibrates in only one direction. So when light passes into the polarizer, light is polarized in a particular direction to pass it. The sample solution under investigation is kept in the polarimeter glass tube. The emerged polarized ray passes through the sample solution to the analyzer. The analyzer happens to be another polarizing prism. The analyzing rotator prism is fixed in such a manner that it can be rotated easily about the axis of the incident light ray. Two situations arise when the analyzing rotator prism is put into action. First, the prism being parallel to the plane of the polarization of the incident light. The net result is the intensity of the light reaching the null detector is maximum. Secondly, the prism being perpendicular to the plane of the polarized light. The net result is the intensity of the light reaching the detector is minimum. That is, when the analyzer is in a position similar to polarizer, it allows the light waves comes from the polarizer to pass through it. When the analyzer is rotated through the right angle, no wave can pass through it and the field view will be dark. When the emerged plane polarized light passes through the sample, which is optically active, it rotates the plane polarized light. Hence, the plane of the analyzer is no more parallel to the rotated plane polarized light. Now the screen looks dark. In order to observe the maximum brightness, the observer will have to rotate the analyzer to make sure that the plane polarized light after rotation becomes parallel to the plane of the analyzer. The observer rotates the axis of the analyzer back either clockwise or anti-clockwise direction depending on the nature of the compound. For clockwise direction, the rotation is defined as positive and called dextrorotatory. In contrast, the counterclockwise direction is defined as negative and called levorotatory. Rotation of analyzer to get brightness back is called angle of rotation. The resulting degree of rotation is a direct measure of the optical rotation of the sample. The correct wavelength for the measurement is precisely selected by an interference filter positioned in the beam in front of the photoreceiver. Biot discovered that the observed rotation is proportional to the length of the polarimeter tube containing the optically active liquid in decimeter and the concentration in gram per milliliter. Observed rotation is equal to constant into length of the polarimeter tube into concentration of the sample solution. Let it be equation 1. In this equation, the proportionality constant is called specific rotation. Rearranging the equation 1, specific rotation is equal to observed rotation divided by length of the polarimeter tube into concentration of the sample solution. Specific rotation is denoted as alpha in the bracket. Bracket tells us just rather than the observed rotation. Alpha is the observed rotation. L, optical path length in decimeter. Here, path length is not measured in centimeter or meter. It is measured in decimeter. C, concentration in gram per milliliter. Even scientists running their own experiment, sometimes they compare their experimental value with the standard one. Just like we have SI unit and IUPAC nomenclature. Likewise, the standard system for the optical activity is the specific rotation. Specific rotation is defined as the number of degrees of rotation of plane polarized light produced by 1 gram of the substance per milliliter. It is the optical rotation for a given number of optically active molecules in the light's wave passed through the sample. This number of molecules the light beam meets is determined by the concentration of the optically active substance, length of the sample cell, temperature and wavelength of the light. Concentration of the optically active substance is higher, the light beam meets more number of molecules of the sample. Length of the sample cell is longer, the more molecules along the way. So light beam means more number of molecules of the sample. Temperature influences density through thermal expansion and may cause changes in molecular structure with effects on the optical rotation. Another influencing parameter on the measured optical rotation is the wavelength of the light. Normally, we use sodium light. D line of sodium 589 nanometer. When the specific rotation of the substance is known, concentration of the substance can be predicted. It is also possible to predict the optical purity of the sample with specific rotation. Here's some example. A student obtained the following specific optical rotation from his measurement. He measured the specific rotation is plus 4.5 degrees. This notation means that the measurement was conducted at 25 degrees Celsius using the D line of the sodium lamp. Lambda is 589.3 nanometer. A sample containing 1 gram per milliliter of the compound in a 1 decimeter tube exhibits an optical rotation of 4.5 degrees in clockwise direction. Now we discuss some problems based on enatiomeric excess. Question number 1. A solution of 28 mg of enantiomerically pure mandelic acid in 1 ml of ethanol was found to have an optical rotation of minus 4.35 degrees when placed in 10 centimeter long polarimeter cell. What is the specific rotation of the acid? We know that specific rotation is equal to observed rotation in degrees divided by length of the polarimeter cell in decimeter into concentration in gram per milliliter. The given observed rotation is minus 4.35 degrees. Length is 10 centimeter. We have to substitute the value for length only in decimeter. So we have to convert the given data in decimeter. 10 centimeter is equal to 1 decimeter. The given concentration of the sample is 28 milligram per milliliter, which is equal to 0.028 gram per milliliter. So putting these values in the expression, we get specific rotation is equal to minus 4.35 divided by 1 into 0.028. This gives minus 155.36 degrees. Question number 2. A sample of 2-bromobutanoic acid has observed specific rotation of plus 9.2 degrees. If the specific rotation of the pure S enantiomer is plus 23.1 degrees, then calculate enantiomeric excess and the percent of each enantiomer in the solution. We know that percent enantiomeric excess is equal to specific rotation of the sample divided by specific rotation of the pure enantiomer into 100. The given specific rotation of the sample is plus 9.2 and specific rotation of the pure enantiomer is plus 23.1. Putting the given values in the expression, percent enantiomeric excess is equal to plus 9.2 divided by plus 23.1 into 100. This gives 40%. What is 40%? An enantiomeric excess. We can take the entire sample as 100%. In that sample, we have 40% pure S enantiomer and another 60% can be racemic mixture. In 60% racemic mixture, we have 30% R enantiomer and 30% S enantiomer. From this we can get a total and we can say 30% of S enantiomer in racemic mixture and 40% pure S enantiomer. Totally we have 70% of S enantiomer. And of course we have 30% R enantiomer in the solution. Hence in the solution we have 70% S enantiomer and 30% R enantiomer.